Week 3, Lecture 2, more on SIR models. We need to talk a little more about SIR models because in order to fit the model to the data from West Africa, we need to discuss how the data can be interpreted and how they can somehow provide us with parameter values. So the central thing is that there is a threshold. If you look at these three equations, S is the number of susceptibles, I the number of infecteds, R the number of removed at any given time. So this is at time t sub I, and then a time dt later is t sub I plus 1. So from one time to the next, the duration is dt, and we can calculate the change by lambda times S times I. They get added to I, but there's also the removals. So obviously the epidemic will only happen if this is positive at the start of the epidemic. If this I is negative at the start of the epidemic, then maybe there are a few infected people, but their number just go down. So what we need for the epidemic to happen is that at the start, this must be positive, and this will only happen when take out I, we divide this whole thing by I is some positive value. So lambda S minus gamma must be positive, which means that the initial S must be larger than gamma over lambda. That is the threshold property. So obviously for the West African epidemic, our parameter values must be such that at the beginning of 2014, the population was larger than gamma over lambda. There is also a duration of infectiousness implied by our model. So the loss rate of infected is gamma I, and that means that every day there's a fraction of infected people being removed, and that is the fraction gamma of all infected people. So if, for instance, gamma was 1 over 10, then every day 1/10 of the ill people would be removed. So if we say that the ill people go step by step, the number of people getting ill on day 1 is equal to the number of ill people being removed at day 10. That means that the duration is approximately 1 over gamma. That is how long people are ill for. In other words, the duration of a person's illness, one person from the time that they start being infectious to the time they stop being infectious, is about 1 over gamma. We say that the duration of illness, or at least the duration of infectiousness for EVD, is approximately 3 weeks, and so 1 over gamma is about 21, and so it's quite reasonable to use 0.05 as our estimate for gamma. It's of course very crude, we're just making rough estimates, we're just getting started. So let's plot a phase plane plot. That will be the number of infecteds versus the number of susceptibles. That will show us, as the epidemic increases, how do the number of the susceptibles and infecteds relate. So as before, we create the function, we set ourselves up to plot, and we run the function. These are values similar to what we had before, so let's see what the phase plot looks like. So here we see that for these values, an initial 2,000 infected people gave us a maximum of infected people a little over 300, and at the end of it, about 400 people had not ever been ill and remained susceptible. So we can change our initial population. Here it was 2,000. If we make it 1,000, let's see what happens. So let's look at this. We start with 1,000 susceptible people and 4 infected, and it just goes down. This is not an epidemic. Even though nearly 100 people got ill, it's not technically called an epidemic if it doesn't increase beyond the initial number of susceptibles. If we make the number of susceptibles very slightly than 1,000, let's see what happens. Let's say we just say 1,010. Well, now it's called an epidemic because it does increase, but really the difference is very slight. So this allows us to estimate the values of gamma and lambda. We've already got our estimate of gamma, now we use it. We estimate lambda using the threshold value. So from the formula for the threshold value, gamma over lambda, we deduce that lambda is gamma over the threshold. The EVD epidemic was very bad. That means the initial population was a lot larger than the number of susceptibles. So we'll just set the number of susceptibles is 1/10 of the initial population, and we know that the initial population of those countries were 22 million. We say that this was our initial susceptible population because there's no reason to say that some of them could not get the disease, that some of them were completely safe. So now we have to go back and we have to set our S0 at 22 million. 22 million. And we have to calculate our lambda, so we're going to cut it from there and paste it here, and instead of lambda being equal to fixed value, we're going to say lambda is equal to gamma divided by 0.1 times S0. And let's see what we get if we use that. 10 million people got ill and everybody got Ebola. So you can see why initially there was such a lot of worry. If these values were correct, then the entire population might have been wiped out. So thankfully, the disease did not end up wiping out everybody. So our choice of parameters is obviously incorrect, and we need to now go back to the data and work out how we can make a better choice of parameters.